All right, so we're going to be going over chapter 6, lesson 6. So we're going to talk about analyzing graphs of quadratic functions. So we're going to learn how to analyze quadratic functions in the form of y equals a times quantity x minus h squared plus k. And we're also going to learn how to write a quadratic function in the form of y equals a times quantity x minus h squared plus k. So vocabulary that we're going to keep in mind is what is vertex form, and I'm going to give you a hint. This right here is vertex form. So this is what we're going to talk about today. So how can the growth of y equals x squared be used to graph any quadratic function? A family of graphs is a group of graphs that displays one or more similar characteristics. The graph of y equals x squared is called the parent graph of the family of quadratic functions. So if we were to study the graphs of y equals x squared plus 2, and y equals quantity x minus 3 squared, notice that adding a constant to x squared moves the graph up, right? So if this is the normal parent function, if you add 2 to this one, right, it moves it up 2 units. And then also notice that subtracting the x by a constant before you square it moves the graph to the right 3 units. So these are the things we're going to be exploring today. So analyzing quadratic functions. So notice that each function from above, the one that we just went over, can be written in the form of y equals x minus h, quantity squared, plus k, where h and k is the vertex of the parabola. And x equals h is its axis of symmetry, because if h is the x-coordinate of the vertex, obviously the axis of symmetry has to go right down the middle. This is often referred to as the vertex form. So this vertex form is very, very useful when we're talking about quadratic functions. So if we were to look at the equation y equals x squared, right, the parent function, it can be written as y equals x minus 0 squared plus 0 because the vertex is at 0, 0. The axis of symmetry is the vertical line that goes where x is 0. Y equals x squared plus 2, or y equals quantity x minus 0 squared plus 2 would have a vertex at 0, 2, and the axis of symmetry would be through 0, right? The vertical line through where x is 0. Y equals x minus 3 quantity squared, or y equals x minus 3 quantity squared plus 0 would give us the vertex at 3, 0. Again, the axis of symmetry goes right through the vertex where x is 3. So this is just a table showing you how those three graphs that we just looked at, how their vertex changes and how their axis of symmetry are affected. So again, these bottom ones are vertex form. And again, look how useful these numbers are at indicating where the vertex is and where the axis of symmetry is. In chapter 4, you learned that translation slides a figure on the coordinate plane without changing its shape or size. So we didn't really go over chapter 4, but the idea is still the same. As the values of h and k change, the graph of y equals a quantity x minus h squared plus k is the graph of y equals x squared translated, right? So the absolute value of h is the number of units h is negative, or the absolute value of h units right if h is positive, and k if k is positive, or k units down if k is negative. So these are the different ways that a parabola can be translated. It can be translated left, right, up, and down. So let's look at an example. If I were to graph a quadratic function in the vertex form, y y equals quantity x plus 2 squared plus 1, and then we were asked to draw its graph. So first, let's analyze the equation, right? This function can be written as y equals x minus negative 2 squared plus 1, because typically it's x minus the h value, right? So we want to write it at x minus negative 2, so we can see that our h value is actually negative 2, and our k value is actually 1. So the vertex, we know that we talked about earlier, is that the vertex has to be located at h and k, right? The x value is h, the y value is k. So since we have our h and k value, we know that this equation must have a vertex at negative 2, 1. And the axis of symmetry obviously has to run through this x coordinate. So the axis of symmetry is at x equals negative 2. The graph has the same shape as the graph of y equals x squared, but is translated 2 units to the left and 1 unit up. Now we're going to use this information to draw the graph. So first we would plot the vertex at -2, 1, right? Then we would draw the axis of symmetry, the vertical line through the vertex, so x equals -2. Third, we would find and plot 2 points on one side of the axis of symmetry, such as -1, 2 and 0, 5. And then we can use symmetry to complete the graph, and it would look something like this, right? We would have plotted the vertex, drawn the axis of symmetry. We could have substituted in some values to find 2 points, and then since it's symmetrical, we would have reflected over on the other side the same 2 points, and that would make our parabola. Again, in vertex form, things are really, really helpful for identifying where a parabola is. So how does the value of a, right, this value out in front of the parentheses before, after x is squared, how does a affect a parabola? Compare the graphs of the following functions. So this first function is y equals 2x squared. B is y equals 1/2 x squared. C is y equals -2x squared. And D is y equals -1/2 x squared. So this red one is our parent function. It's just the normal y equals x squared function, right? That normal parabola. If I look at A, well, what happens if I take that same equation and just multiply it by 2, right? That would be this blue one here, right? So this blue one looks to be narrower, right? It seems to be steeper or climb faster, right? So that's what multiplying by 2 does. B takes that same parent function and multiplies it by 1/2. Well, look what happens to the function, right? Comparatively to the normal parent function, the red one, it gets wider, right? It's a wider function. It doesn't increase as fast. It takes longer to increase, which makes it wider. And then let's see, C takes the parent function and multiplies it by -2. Well, here's C down here, right? So again, it's narrower than the red one and it's pointed down, right? It opens down instead of opening up. Y equals -1/2 x squared is this green one. And again, it is wider and opens down. So these are some observations we want to make here. All of the graphs have a vertex at 0, 0, so multiplying did not change the location of the graph as far as the vertex goes, and its axis of symmetry was still right down the middle at x equals 0. So that a value doesn't affect the translation of the graph. It doesn't move it left or right or up and down, but it does seem to change the shape of it and what direction it goes in, right? So notice that when I multiplied by a positive, right? +2 or +1/2, those are what are known as dilations, right? They make the graph either get narrower or wider, right? Multiplying by 2 made it get narrower because it increased at a steeper rate. And multiplying by 1/2 made it get wider because it increased at a slower rate. And then when I multiplied the graphs by -2 or -1/2, those were just reflections of the other ones, right? So +2 or -2 were just reflections of each other. So when I multiplied by +2, it was opening up. When I multiplied by -2, it was opening down. When I multiplied by -1/2, it opened up. When I multiplied by -1/2, it opened down. So positives make it go up, negatives make it open down. So the numbers, whether they're bigger or numbers smaller than 1, is a dilation, whether it goes narrower or wider. And when you multiply by a negative, that gives it a reflection. So it makes it either open up or down, depending if it's positive. So if we were to change the value of a in an equation, that can affect the direction of the opening and the shape of the graph. So if a is positive, the graph opens up. If a is negative, the graph opens down. If a is, or the absolute value of a is greater than 1, that means the graph gets narrower, right? So if you're multiplying by a positive or negative number that's bigger than 1, the graph gets narrower, right? Now, if that, whether it's positive or negative, if it's less than 1, so any fraction essentially that's less than 1, between 0 and 1, as long as it's that will make the graph get wider, right? Because it won't increase as fast. So here's the concept summary here. Whenever I'm examining a quadratic function in vertex form, h and k represent where the vertex is, and obviously the h value is going to represent where the axis of symmetry is. K, right, the outside constant there, that will determine if it translates up or down, right? A k value that is positive will make it translate up. A k value that is negative will make it translate down. Let's talk about h. So as h changes, if h is positive, right? If h is positive, it will actually make it move to the left. And if h is negative, then it'll make it move to the right. Oh, I'm sorry, I have that reversed. If h is negative, it'll move to the left, and h is positive, it'll move to the right. Where it does get a little bit confusing is it's x minus, like if it was x minus 3, that h would be a positive value, so x minus 3 moves it 3 units to the right. And like say it was x plus 2, x plus 2 would mean that this is x minus -2, which -2 makes it move to the left. So that's where it gets a little bit confusing. Again, you'll be able to see it in some examples later on. And remembering that the a value impacts which direction it opens. If it's positive, it opens up. If it's negative, it opens down. And the direction and the shape of the parabola is also affected by a. So if a is a value that is larger than 1, it's going to get narrower. And if an a value is between 0 and 1, right, a number smaller than 1, it's going to get wider. So those are the big key concepts to take away there. So when we're writing a quadratic function in vertex form, if you're given a function of the form y equals ax squared plus bx plus c, you can complete the square to write the function in vertex form. So here's an example. If you write y equals x squared plus 8x minus 5 in vertex form and then analyze it, you should be able to understand what the characteristics are of this parabola. So if I take the original equation, I notice that it's not a perfect square, right? But I can go ahead and actually use the completing the square method, right? This is the one we practiced in a previous lesson. So if I wanted to make x squared plus 8x into a perfect square, I would want to add 16. How do you know where to add 16? Well, you take 8 divided by 2 and square it. 8 divided by 2 is 4, and 4 squared is 16. Now I have a perfect square here, right? This will give me x plus 4 times x plus 4, right? That perfect square trinomial. Now, in order to be able to do this, because it's an equation, if I add 16 inside of the parentheses, I need to subtract 16 on the outside in order to balance it out, because I need this equation to remain equal, right? So if I add 16 inside and subtract 16 outside, it's like if I added 0, right? It's balancing the equation. Here, I'm going to go ahead and simplify, right? So like we said, we created a perfect square trinomial here. So that's x plus 4 squared, right? X plus 4 times x plus 4 gives me this. And then if I have minus 5 minus 16, that makes minus 21. And now I can see that I have it in vertex form. So since this function is now in vertex form, again, this is what I was talking about before, whether this value moves it to the left or right. Really, your vertex form is supposed to be x minus h squared plus k. So here I can see that my h is actually -4, right? Because it's x minus h. So h has to be -4 in order to be equivalent to +4 there. And then my k value is -21. So I can see now that since my h value is -4, it's going to move my parabola 4 units to the left. And this -21 will move it 21 units down. So the vertex will be located at -4 and -21. The axis of symmetry has to run through that vertex, so it's going to be the vertical line x equals -4. Since a equals 1, the graph still opens up, right? It's still a positive. positive 1. So it's still going to open up and has the same shape as y equals x squared, but is just translated 4 units to the left and 21 units down. When writing a quadratic function in which the coefficient of the quadratic term is not 1 in vertex form, the first step is to factor out that coefficient from the quadratic and linear terms. Then you can complete the square and write it in vertex form. So here we're going to deal with a problem. Notice how it's not 1x squared, it's negative 3x squared. So we're still going to follow the same strategy, except we're going to factor it out in order to complete the square. So take the original equation. If I divide negative 3 out of all 3 terms, right, factor out negative 3. Actually, you only have to do it to the first 2 terms. If I factor out negative 3, right, it's going to leave me with x squared minus 2x, because negative 3x squared divided by negative 3 is 1x squared, and positive 6x divided by negative 3 is negative 2x. We're going to leave that negative 1 out there because that's not going to help us complete the square. So now we're going to go ahead and complete the square. So in order to have a perfect square trinomial, again, you're going to take the middle term and divide it by 2 and square it. Negative 2 divided by 2 is negative 1, and negative 1 squared is 1. So I have to add 1 here. Again, in order to balance it out, whatever I add on the inside, I have to subtract on the outside. Now, here's the deal. I didn't actually add just 1 because this is actually negative 3 times 1. So really it's like subtracting 3. So I need to make sure I do the same thing on the outside. Negative 3 times 1, right? So this is going to make it balance out. So again, this is the equivalent of subtracting 3, and this will be the equivalent of adding 3. So again, they will balance each other out in the equation. Now it just takes time to simplify it. So now I have to rewrite this as a perfect square. So it's going to be negative 3 x minus 1 squared. And then I'm going to go ahead and simplify this part. So this is going to be minus 1 plus 3. So minus 1 plus 3 is plus 2. Now you can see it's in vertex form. So again, we can analyze this and figure out what the graph should look like, right? So we now know that the vertex should be at 1, 2, right? My h is positive 1. My k is positive 2. So now I know that that's where the vertex is going to be located. So if the vertex is located at 1, 2, that means the axis of symmetry is at the vertical line at x equals 1. And since my a value is negative 3, I know it's going to open down now because it's negative. And the fact that it's a number larger than 1, right, the absolute value is larger than 1, that means it's going to make it get narrower, right? It will get narrower. So it's going to point down. It's going to be narrower than the normal parabola for y equals x squared. So again, it's also going to be translated 1 unit to the right and 2 units up. So this is what my parabola will look like. So again, I know where the vertex was. The vertex was at 1, 2. And then I know that it's pointed down and it's narrower than the normal one. Again, you could get 2 points just by plugging into x values, and then you could reflect it on the other side. All right, let's take a look at some more. So if the vertex and one other point on the graph of a parabola are known, you can write the equation of the parabola in vertex form. So here's an example. If you were to write an equation for a parabola whose vertex is at negative 1, 4, and passes through the point 2, 1, you can use this information and the standard form or the vertex form of a quadratic. So since we know the vertex is at negative 1, 4, we know our h value has to be negative 1, and our k value has to be 4. And since it goes through the point 2, 1, then we know that our x value has to be 2 when our y value is 1. So we can substitute all of these values into vertex form and solve for a, solve for the missing value. So again, here's our vertex form. We know that h and k are our vertex. So here's our h, where we'll put negative 1 in. Our k, we'll put 4 in. And since they gave us a point that goes through our parabola, this is just an x and y value. So we can put 2 in for our x value, 1 in for our y value, and so all we'll be left with is the a variable, which we can solve for. So again, substitute all the values in, and then we go ahead and simplify, right? 2 minus negative 1, that's like adding 1, so 2 plus 1 is 3. 3 squared is going to be 9. And then I'm going to go ahead and solve the equation now and solve for a. So I'm going to start by subtracting 4 from each side. So I get negative 3 equals 9a. Divide both sides by 9, and I get negative 1/3 equals a. So now that I know a is negative 1/3, now I can go ahead and write my vertex form equation. Okay, so again, in order to write a vertex form equation, we already know our h and k. We have now solved for a, so those are the only values we need to put in. So the equation for this parabola in vertex form is going to be y equals negative 1/3 quantity x plus 1 squared plus 4. So this is how you can write an equation if you're given the vertex and a point. And if you wanted to check this, obviously you can take this equation and you can graph it, right? You can use a program like Desmos and graph it, check it to see if it works, right? So here's our equation, here's our graph. It goes through the point -1, 4 for its vertex, and it passes through the point 2, 1. So clearly it fulfills the information that we were given. All right. Thank you guys for watching. Let me know if you have any questions.